Myself, Panaka Aditya from 3rd Sem CSE A section. My presentation topic is three-state buffers. So the topics that are going to be covered in this presentation are an introduction to buffers, tri-state buffers, logically equivalent circuit of two buffers connected together, and applications of three-state buffers. What is a buffer? A digital buffer or a voltage buffer is an electronic circuit element used to isolate an input from an output. That is, if an input is given, it just stores the input and passes it on. The digital buffer is a non-inverting device and will therefore give us the Boolean expression of Q equal to A. Then we can define the logical operation of a single input digital buffer as being Q is true only when A is true. A truth table is given here. The symbol of a digital buffer is also given. In this symbol, A is the input and Q is the output. Therefore, Q will be equal to A. Tri-state buffer. As well as the standard digital buffer that was seen in the previous slide, there is another type of digital buffer circuit whose output can be electronically disconnected from its output circuitry when required. This kind of a buffer is known as three-state buffer. This means that when a buffer is functioning, if we don't want the output at a particular time, the output can be disabled using the enable input B. The equivalent circuit for this is given in the next slide. Figure A shows a three-state buffer and its logical equivalent. When the enable input B is 1, that is the enable input B over here, if this is 1, then the output C will be equal to the input A. When B is 0, the output C acts like an open circuit. Here, from this equivalent circuit, we can see that B is acting like a switch. Therefore, when the switch is open, that means that when B is 0, this will be an open circuit. This is known as a high Z or a high impedance state of the output because this circuit will offer a very high resistance or impedance to the flow of current. In figures A and B, the enable input B is not inverted. So the output of C will be enabled only when B is equal to 1. Figure A is a normal three-state buffer, whereas in figure B, we can see that the output C is inverted. So therefore, only when A is 0, we get that C will be 1. When A is 1, C will be 0 as C is inverted. This will happen provided that B is 1, or if B is 0, it will result in a high impedance state. In case of figures C and D, we can see that the enable input B is inverted. So this means that if B is 1, the circuit will be in a high impedance state. Only when B is 0, the circuit is functioning. In case of figure C, the output C is not inverted. Therefore, when A is 0, output will be 0. When A is 1, output will be 1, provided that B is 0 as it is inverted. In case of figure D, both the enable input B and the output C are inverted. Therefore, for the circuit to function, B must have a value of 0, and to get an output as 1, A must be having an input as 0. Logically equivalent circuit of two three-state buffers. In the following figure, the output of two three-state buffers are tied together. Therefore, when B is 0, the top buffer is enabled. The top buffer is enabled when B is 0 because the enable bit B for the top buffer is inverted. As it is inverted, the top buffer will be enabled only when B is 0. So in this case, the output D will be equal to the input A. When B is 1, the lower buffer is enabled, that is the buffer C or the buffer with the input C is enabled because here the enable bit is not inverted. Therefore, when B is 1, lower buffer is enabled. In this case, D will be equal to C. Here, D will not be equal to A as the enable input B for A is inverted. So therefore, when B is 1, this will be 0. Therefore, when B is 1, output D will be equal to C. This is logically equivalent to a 2:1 multiplexer. When we connect two three-state buffer outputs together as shown in figure B. If one of the buffers is disabled, the combined output F is same as the other buffer output. If both the buffers are disabled, then the output is high impedance state. If both buffers are enabled, a conflict can occur. If A is 0 and C is 1, we do not know what the hardware will do. So the F output is unknown. If one of the buffer inputs is unknown, the F output will also be unknown. The table in figure B summarizes the operation of the circuit. Applications of buffers. A gate can only be connected to a limited number of other device inputs without degrading the performance of a digital system. A simple buffer may be used to increase the driving capability of a gate output. The following figure shows a buffer connected between a gate output and several gate inputs. Because no bubble is present at the buffer output, this is a non-inverting buffer and the logic values of the buffer input and output are the same. That is, F will be equal to C. Each of these devices is capable of sending or receiving data to each other onto the single data bus at the same time, creating what is called a contention. Contention occurs when multiple devices are connected together because some want to drive their output high and some low. If these devices start to send or receive data at the same time, a short circuit may occur when one device outputs to the bus a logic 1, the supply voltage, while another is set at logic level 0 or ground, resulting in short circuit condition which will cause damage to the devices as well as cause a loss of data. Digital information is sent over these data buses or data highways either serially, one bit at a time, or it may be up to 8 or more wires together in a parallel form, such as in a microprocessor data bus, allowing multiple tri-state buffers to be connected to the same data highway without damage or loss of data. Coming to the second application, a multiplexer may be used to select one of the several sources to drive a device input. For example, if an adder input must come from four different sources, a 4:1 multiplexer may be used to select one of the four sources. An alternative is to set up a three-state bus, which will be done by using three-state buffers to select one of the sources. In this circuit, each buffer symbol here actually represents four three-state buffers that have a common enable signal. Coming to application number 3, integrated circuits are often designed using bidirectional pins for input and output. Bidirectional means that the same pin can be used as an input pin and as an output pin, but not both at the same time. To accomplish this, the circuit is connected to the pin through a three-state buffer as shown in the following figure. When the buffer is enabled, the pin is driven with the output signal. When the buffer is disabled, an external source can drive the input pin. So with this, we come to the end of our presentation. Thank you.